In today's session, let us see another problem, which is called as optimal binary search trees. And let us discuss on how optimal binary search trees can be generated using dynamic programming approach. So let me first give you a refresh on binary search trees. A binary search tree is a binary tree in which the nodes are arranged in a specific order. And hence the binary search tree is also called as ordered binary tree. And a binary tree is called as a binary search tree if the following properties are satisfied. The properties are recursively applicable on the left and right subtrees of the root. So this is a binary tree. And if I want to call this as a binary search tree, then two properties have to be recursively satisfied by every node in the tree. And what are those properties? If there is a root node with some value 30, then all the values in the left subtree must be less than 30. All the values in the left subtree should be less than 30. And all the values in the right subtree can be greater than or equal to 30. And this property is recursively applicable to all the nodes in the left subtree and all the nodes in the right subtree. That is, if you take the left subtree itself, only the left subtree I am taking here, then this will become the root node. Then this will be the left subtree and this will be the right subtree. Now, the values in the left subtree must be less than 15 and all the values in the right subtree must be greater than or equal to 15. So as such, every node in the tree must satisfy these two properties, that all the values in the left subtree must be less than the parent. All the values in the right subtree must be greater than or equal to the parent. So if these properties are satisfied by each and every node in the binary tree, then such a binary tree is called as a binary search tree. And the application, the major application of binary search tree is searching. Right? So whenever you are storing some values or some data in the form of a binary search tree, then it takes only log n amount of time for searching, log 2n amount of time. That will be the time complexity of the search if you are maintaining the data in the form of a binary search tree. So basically, whenever searching operation is the most important operation and you want to maintain a database to support efficient searching, then you'll maintain the data in the form of a binary search tree, and hence it supports the search process with efficient time complexity of log 2n. Now say, for example, I have three values here, 10, 20, and 30. These three values, I can call them as values, I can call them as data, but here I am going to call them as keys. So there are three keys, and these are to be stored in the form of a binary search tree for efficient searching. Now, satisfying the rules of the binary search tree, if these three keys have to be stored, then there are many different BSTs that can be formulated. You can store the same 10, 20, and 30, these three values, in the form of a binary search tree, and you are able to formulate different binary search trees. So you can see here, I have taken 10 as the root. After taking 10 as the root, then I have taken 20 as the right child. This is because 20 is greater than 10, and all the values that are greater than 10 should form the right subtree. So 20 is inserted here. Then the third value, which is 30, will be the right child of 20, because again 30 is greater than 20. So 30 will be taken as the right child of 20. So this is one binary search tree that I have formulated. Now, how I have generated this binary search tree, I have taken a series of decisions. I have totally taken here 3 decisions or 2 decisions, in which among the keys that are available, 10, 20, and 30, which of these 3 values must be made the root node? So I have made my first decision here that 10 will act as the root of the tree. So first decision is made by considering all the 3 values and deciding which value will act as the root node. Further, once this is done, I have 2 remaining values, 20 and 30. Now, among these 2, which of them should be made the right child of the root? Here, I can write 20. Or I can also write 30. Because both 20 and 30 are greater than 10, I'll make them as the right child. So here I have made a decision that 20 will be the right child of 10. Then the left out value, which is 30, will be made the right child of 20. So I have taken a series of decisions here. In the same way, I can formulate another binary search tree with the same values. But the parent-child relationships are something going to change. So 10 is made the root of the tree. Further, another decision is taken. 30 has come here. Then finally left out, which is 20. 20, I have made it the left child of 30. Because 20 is less than 30, it will go into the left subtree. So 2 binary search trees with different parent-child relationships I have formulated. And for formulating each tree, I have made a series of decisions. And whenever you are able to solve a problem by making a sequence of decisions, then you can solve it by using dynamic programming. That's the first criteria that you have to consider to decide which type of problems can be solved by using DP. So whichever problems can be solved by making a sequence of decisions, those problems can be solved by using DP. Further, you are going to divide a bigger problem into sub-problems, and each sub-problem must hold the principle of optimality. Then only again you can solve the problem by using DP. So here for now, we are making a series of decisions. That is one of the property of the problem that can be solved by using DP. So as such, I have made different decisions and I have totally formulated 5 binary search trees. So you can see here, this binary search tree, I have decided that 20 will be the root of the node. 20 will be the root of the tree. It will act as the root node of the tree. Then the remaining values 10 and 30. 10 is less than 20, so I have made it the left child. 30 is greater than 20, so I have made it to the right child. As such, the third series of decisions, starting with 30 as the root node and remaining decisions I have made. So I have totally 5 different binary search trees given the 3 values. So how many such binary search trees can I formulate? How many BSTs can I formulate? given n number of values, you can formulate many number of BSTs, which is equal to 2n factorial divided by n plus 1 factorial into n factorial. This will be the number of BSTs that you can formulate given n number of values. Now, what is the efficiency of each of this BST? So the cost of the BST is equal to the average number of comparisons done for searching. So BST main application is searching. So whenever I have to search for a key, how many number of comparisons do I have to make? And if I am making n, I am searching for n keys, how many number of comparisons on the average do I have to perform? That will determine the efficiency of the tree. That will determine the cost of the tree. So how come I calculate that? If I take the first BST, I have 3 keys. Say for example that I want to search for key number 10. I have to search for key 10. The search key is 10. Now, how many number of comparisons do I have to make? I have to make only one comparison because 10 is the root node. So always you'll start searching from the root. So once you start searching at the root node, there itself, at the root itself, you have found the 10 value. So you'll make only one comparison. So for searching 10, I have made only one comparison. Then, if I want to search for the key value 20, again, I'll go with the same binary search tree. I'll start searching from root itself. So I'll compare with the root node. I'm searching for 20, but the root node is consisting of 10. If I'm not able to find 20 at the root, I'll try to traverse to the bottom of the tree. Now, what will I do? I'm going to come down. I have made here at the root, I have made a comparison and I did not find 20. Then I'm coming down the tree. Now I'm making my second comparison here. I have found 20 there. So my search is successful. Now, if I have to find 20 in the given BST, how many number of comparisons I have made? I have made 2 comparisons. Now, I'll have to search for 30. So again, starting at the root, I did not find 30 at the root. So I've made one comparison and I found out that 30 is not there. I'm traversing down the tree. I'm making another comparison and I'm checking whether 30 is there or not. It is not there. Then I'm still coming to the bottom of the tree and I'm making another comparison here, third comparison, and I'm finding 30 there. So to find the key 30, how many number of comparisons did I make? I make 3 comparisons. Okay. All the 3 key values, I have found out how many comparisons are needed to find the key. Now, what is the average? Average will be equal to 3 plus 2 plus 1 by 3. This is the average. This is the formula that I have written here. Okay, so now with the value is 2, the average number of comparisons or the cost of the first BST is 2. So in the same way, I'm going to find out the cost for the remaining BSTs, and the values were like this: 2, 2, 1.6, 2, and 2. And now among all these BSTs that I can formulate, I can generate for the same given problem, which one can I call it as optimal binary tree? An optimal binary search tree is the one which has least cost, which has minimum cost. So given a binary search tree, it is said to be optimal if it has minimum cost. Now, among all these 5 BSTs, what is the BST that has minimum cost? This one. So this is my optimal BST. Now, what is the advantage of optimal binary search tree? The advantage of optimal binary search tree is it takes minimum average number of comparisons. It takes average number of comparisons in an optimal BST are minimum. Now, the challenge is that you are going to use dynamic programming approach. You'll be given a set of keys. You have to generate an optimal binary search tree, which has minimum cost. So this is an optimization problem. Generating an optimal BST is an optimization problem, and it is an minimization problem. Because we are talking about the cost of the tree should be minimum. So it is a minimization problem. Now, in the before problem here, I have taken 3 keys, 10, 20, and 30, and I have assumed that all the 3 keys have the same probability of search. The same probability of search. That is, the value 10, the value 20, and the value 30. All of the 3 values will be searched equally in the database. But practically, which is not possible, each value might be searched for different number of times. 10 may be more frequently searched. 30 may be least frequently searched item. That may be possible. If you take a search engine like Google, these days, people may be searching for corona-related news. So those news, corona-related news, are most frequently searched news these days. Right? So depending upon that, some items may be more frequently searched. Some items in the database may be less frequently searched. So considering practically that different keys may be searched for with different frequencies, or you can represent it as probabilities. That is also you can represent. So each key, it will have its frequency. Frequency will indicate how many times it is being referred in the database. Now you can see here, for the items 10, 20, 30, frequencies are also given. The item 10 is you referred to, searched for 2 times out of 7 times. Total searches are 7. So the total number of searches are 7. Among 7, every 7 searches, 10 is being searched for 2 times, 20 is being searched for only 1 time, 30 is being searched for 4 times. This is the frequency of the search. Out of every 7 times, this is the frequency of search for the items. So now I can say 30 is the most frequently searched item. 20 is the least frequently searched item. Now, these frequencies, you can represent them as numbers like this, how many times they are being searched for, or otherwise, you can also represent it as a probability. Instead of frequencies, I can represent it as probabilities. So probabilities will be equal to 2 by 7. It will be a value. Each probability value will be between 0 and 1. So it will be 2 by 7, 1 by 7, and 4 by 7. In this way, you can also represent the probabilities of the items, or you can represent as frequencies of the items. Now, anyway, each item has its own frequency, has its own probability for search. Then again, there will be successful searches, there will be unsuccessful searches. Okay, so what is the successful search? Successful search is where if the user tries to search for 10, 20, and 30, the keys that are available in the tree. If the user is trying to search for the keys available in the tree, it is a successful search. Instead, if the user is trying to search for some number 15, 15 is not there here, it's not there, then it will be an unsuccessful search. Okay, now we'll talk about only successful searches and the probabilities. So now again, I'm taking the same binary search trees, 5 BSTs, but now for calculating the cost of the tree, I am also going to consider the frequencies as well. The frequencies also. Now, what is the cost of the tree? Let us see. So if I'm going to search for some item 10, I'm searching for some item 10. Now, here is the item 10. I could find the item 10 at the root itself. So how many comparisons did I make? I made one comparison to search for 10. Now, how many times? What is its frequency? Its frequency is 2. So what is the cost of searching the key 10? The cost of searching the key 10 is 2. 1 into 2 is equal to 2. So the cost of searching the key value 10 is 2. In the same way, I want to search for an item 20. I want to search for an item 20. Now, what is the cost for searching item 20? How many number of comparisons should I make? I have to make 2 comparisons to find 20. Then, what is the frequency? The frequency of the item 20 is 1. So what is the cost of searching the item 20? It is 2. So it is 2. Then cost for searching the item 30. How many number of comparisons should I make? I'll make 3 comparisons. From root node to 30th node, I'll have to make 3 comparisons to find 30. And what is the frequency of the item? Which is equal to 4. Now, what is the cost for searching 30? It is 12. Now, what is the average of searching? 12 plus 2 plus 2. 16 by 3. So this is 12 plus 12 by 2, which is equal to 16. 16 by the average is 3. So this is what I have written here. The cost of the tree is 16 by 3, considering the keys along with their frequencies or along with their probabilities, whatever it is. Now, this I'm talking about only successful searches. Unsuccessful search may also be possible. I may want to search for an item 15. 15 I want to search. Now, I want to search for some item 15. How many number of searches I am going to make? I'm going to make the first comparison here and see if 15 is there. No, it is not there. I'll go to the right side. I'll make second comparison here. Is 15 there? It's not there. So I have to go to the left side actually. Left subtree, left child I have to traverse because 15 is less than 20, but left subtree is not there. The left subtree for 20 is empty. So how many number of comparisons did I make to find out that 15 is not there? It's an unsuccessful search. I made 2 comparisons. Right? So as such, what is the total cost of the tree? The total cost of the tree is the cost of successful searches plus the cost of unsuccessful searches. That will be how the cost of a binary search tree will be defined. The cost of a BST is equal to the cost of successful searches plus the cost of unsuccessful searches. Now here I am trying to consider only successful searches. I am trying to calculate the cost. So now 16/3 is the cost of the first binary search tree. And these are the costs of the remaining BSTs. Now tell me, which is the optimal binary search tree? This is the optimal binary search tree because its cost is less than the others. So if we are not considering frequencies or probabilities, this was the optimal binary search tree. But if we are considering frequencies for each item, this is the optimal binary search tree. Okay, now defining the problem, optimal BST's problem. Given a fixed set of keys, a binary search tree has to be created. And it is possible that different binary search trees with different costs can be constructed. And the efficiency of a BST is calculated in terms of the cost of successful searches and the cost of unsuccessful searches. And the challenge, the objective function is to generate an optimal BST for which the cost function is minimum. And for generating such optimal BST, we are going to make use of dynamic programming approach. We are going to devise a DP based algorithm for generating an optimal BST. So we are going to make some changes here for the BST, for the binary search tree, so that we can apply dynamic programming approach for generating an optimal tree. So we are going to add a few dummy nodes. We are going to add a few dummy nodes. These are called as dummy nodes, or they may be called as fictitious nodes. Say, for example, this is the binary search tree with the given keys. We are going to add a few dummy nodes as leaf nodes. Now here you can see I have added a few dummy nodes for each key leaf node. So now once you add these dummy nodes, then these 10 and 30 will become internal nodes of the tree. Previously, these were the leaf nodes. 10 and 30 were leaf nodes. But instead, what we are going to do is, we are going to make them as internal nodes. If we want to make them as internal nodes, they must have some childs. So I'm going to create dummy child nodes. Each parent will have 2 dummy child nodes. So I have added these dummy nodes at the bottom of the tree. Now this E0, E1, E2, E3 are now becoming leaf nodes. 10 and 30 are now becoming internal nodes. This is the motto behind adding the dummy nodes. I want to make all the keys as internal nodes. That is, I want to make all the successful searches should end at the internal nodes. All the successful searches. What is a successful search? It is the one when I try to search for 10, 20, or 30. Because they are there in the tree, it will be a successful search. If I try to search for any other number other than 10, 20, 30, I want to search for any other number, then it will be an unsuccessful search. Now, why I'm adding dummy nodes here is, I want to make sure that all the successful searches should end should terminate at the internal nodes. All the unsuccessful searches should end at the leaf nodes. So all the internal nodes are representing successful searches. All the leaf nodes are representing unsuccessful searches. So for this scenario, for making this to happen, that all successful searches shall end at internal nodes, I'm going to add some extra nodes to the tree, and these are called as dummy nodes. Right? And now, how many number of dummy nodes do you have to add? If there are n internal nodes, then there will be n plus 1 dummy nodes, which will be leaf nodes. These dummy nodes will always be at the bottommost level of the tree. So they will be leaf nodes. So here there are 3 internal nodes, 20, 10, 30. These are the 3 internal nodes. So I have added 4 leaf nodes as dummy nodes. So I'm making sure that all these successful searches end all at the internal node, and all the unsuccessful searches will end at the leaf nodes. Now, what is this E0, E1, E2, and E3? These are leaf nodes and dummy nodes that we have added extra into the tree. Now, what are this? E0 is not a single key, but it is a set of keys. Each dummy node that we have added represents a set of keys. So this E0 represents a set of keys, not a single key, but a set of keys. Whereas if you see all the internal nodes, 20, 10, 30, these are the internal nodes, they represent a single key. But whereas dummy nodes represent a set of keys. Set of keys and a bunch of keys. Now what are those bunch of keys? Now E0 represents an unsuccessful search. Unsuccessful search ante what are all the values that make an unsuccessful search of E0? So for that, I'm going to consider, when do you come here at this point, starting from root node, you go on traversing, when do you come down to E0? You come down to E0 point when the search key you want to search for is minus infinity to 9. That is, you want to search for some value less than 9. Then you'll come from root to E0. You'll traverse from root to E0. Say, for example, I want to search for some number 9. I'll start searching at root. I've made a comparison. 9 is not here. Then I'll go to the left side. I'll go to the left side because 9 is less than 20. So I'll go on to the left side. Now, I'll make another comparison here. 9 is not there. Then I'll go to the left side because 9 is less than 10. So I'm going to travel to the left subtree. And because this is a leaf node, I'll stop the comparison here and I'll say that 9 is not found in the tree. That is, 9 is an unsuccessful search. So when do you come to E0? When do you come to this place while traversing? You'll come to this point E0 whenever you are searching for some value which is less than 10. You'll come here. You'll end at E0. What is less than 10? Any value from infinity to 9. So I can write this less than 10 as minus infinity to 9. So it's not a single key. Leaf node E0 is not a single key, but it is a set of keys. It is a set of keys. In the same way, E1. it will again consist of another set of keys. And what are those set of keys? When do you end your search? At E1. Those are the values between 10 and 20. 10 and 20. All the values between 10 and 20. That is 11 to 19. In the same way, E2, 21 to 29. E3, 31 to plus infinity. These are the values or the keys which represent unsuccessful search. So the keys that represent successful search are 10, 20, and 30. The keys that represent unsuccessful search are these bunch of keys, which are represented as E0, E1, E2, and E3. So now I'll try to write a generic formula for some EI. What is EI? Say, for example, we are trying to have a binary search tree where all the set of keys are A1, A2, and so on up to AN. Up to AN. These are the bunch of keys in the binary search tree. Now, what are the dummy keys? For that, we'll try to write E0. E0 will be equal to all the values which are less than A1. What are all the values which are less than A1? Minus infinity to less than A1. So that is what I have written here. E0 is equal to all keys where minus infinity to less than A1. Then remaining sets, in between sets, E1, E2, E3, and so on. These each dummy node EI will consist of all the keys X between AI and AI plus 1. Then the last dummy node, rightmost dummy node, that is nothing but I am talking this as E0. In between all are EI, and the last one is EN. So EN will be equal to 31 to plus infinity. That is the last number, AN to infinity. So these are how you are going to represent the unsuccessful keys. And all of this we are doing to make sure that all the successful searches end at any one of the internal nodes, and all unsuccessful searches should end at the leaf nodes. So this will be the session. We will continue solving the problem in the upcoming session also.